Sorry, Aiden. Okay. So, we are on day 3. But before we start with day 3, alright? Before we start with day 3, go to this. Go to this. Turn to your activity series side. That's your kind of list with the arrow. Everybody have it? Looking at it? Of the 5 types of reactions that we've learned about, which one do we use the activity series with?
A single replacement?
A single replacement only. I don't know if you need to write that down somewhere, because some of you probably need to because you weren't able to answer that. Your single or your activity series chart is used with single replacement reactions only. So from now on any of your homework, on your quiz, on your test, if you are looking at a single replacement reaction, you had better be checking what? To see if what? If the reaction actually takes place. You'll follow me there? So just because I don't come out and explicitly tell you to check if the reaction takes place, you still need to. Are you following me with that? You've got to check it. Now on the back side is your solubility chart or your solubility rules. Have a look at that. We will be using this today. This is only for double replacement reactions. So if you're looking at combustion, should you be looking at this at all?
No.
If you're looking at synthesis, should you be looking at this at all?
No.
That's what I mean. That's what I'm trying to get across right now. All right? Double replacement, single replacement.
Okay.
That's what this paper is used for. You will have this on your test for this semester. For this semester.
I don't like how you're saying that.
Sorry. Okay? Here we go. So, to start off, we are going to be talking about double replacement reactions. Now, we've already talked about what they are. You have an A and a B plus CD, and then they replace each other. Okay? This is a little bit different lettering, but it's still, instead of B and D there, they put the X and the Y. All right? In our slides from the other day, it had A, B, C, and D. It's the same concept. Okay? So we have 4 things reacting. Now, most of the time it's going to be different elements. However, what else can one of these letters represent? What are some things that we know that always stay together? Polyatomic ions. So you could have an element polyatomic ion, and that's still a double replacement even though you have multiple elements in there. Polyatomic ions act as one single element for the most part. That's what I'm trying to say to you right now. All right? So here we go. Here are some examples. How do we know what goes into the products? Okay? So let's say I just give you the reactants and you need to figure out what the products are, and you will. How do we do that? Well, the thing is, your metals stay the same, and what happens is your anions are going to switch. Okay? Because this is ionic, we need to have ionic over here. So you still need to have a metal, non-metal, metal, non-metal. Yes?
Yeah, it's just that, like, I know you just said that the metals stay the same, and like, it says, like, the non-metal's supposed to switch, but, like, that end result kind of says the exact opposite, where the non-metals stay in the same place and the metals switched.
Yeah, I don't like that.
Okay.
So I'm going to keep the metals the same.
Okay.
Is that all right with you? So, yes, that's fine. Just know that in our slides from last unit, it says that your anion switch. So I'm sticking with that.
Okay.
Okay? Yes, thank you for pointing that out. That Aiden. Okay? So your anion switch. If you want to keep, I don't care which way, in your products you need to know that you have a metal and a non-metal plus a metal and a non-metal. However, what is your one cation that is a nonmetal?
Hydrogen?
Hydrogen. Hydrogen most likely is going to form what?
An acid?
Okay? So when you have acids, you got to be thinking that hydrogen, yes, it's a nonmetal, but it also has a plus charge, which makes it a cation. Okay? So your hydrogen will also be forming with a nonmetal. All right, we'll do an example. An example of that coming up. All right? But that's how we write the products for double replacement. Okay? So when I look at your homework, and Aiden, I just saw your homework real quick when you came up and showed me, you didn't know how to do it, and so this is why I'm making a point of this. I shouldn't see over here Na plus K. Why is that?
Is metal and metal?
Na, sodium plus potassium. What's wrong with that?
That's a metal and a metal.
A metal and a metal. Okay? You need to pair a metal with a nonmetal. Does that make more sense now? You need to pair a metal with a nonmetal, and then your other one should be a metal with a nonmetal. Right, Jacqueline? You good? You stand up. Okay? We're not going to do this slide because it's combustion, it's out of place. And so just like for single replacement, do all single replacement reactions occur?
No?
No, you figured out, right, with activity series, that a handful of them, some of them, not all of them, will not actually react. There'll be no reaction, right? The same thing is going to happen with double replacement reactions. So now your question is, how do we figure that out? If the activity series is just for the single replacement, how do I figure out if a double replacement is going to occur? And here are your steps. Number one, actually write out the products as if they are going to happen. In single replacement, if you go to kick one out and it doesn't work, you don't even need to write out the products. You just write out no reaction. In double replacement, you do need to write out both of the possible products. Okay? From there, here's where it starts to get to be the new stuff. Using solubility, determining if any of the combinations are soluble. Soluble is going to mean it is aqueous. It's going to form a solution. You need to know this. If soluble products are formed, if only soluble products are formed, that means in your products, they are both aqueous, then a double replacement will not occur. So that answers all your curious little minds out there of what happens. How do I know if it's not going to happen? Both of your products are going to be aqueous. Okay? If at least one insoluble product is formed. Insoluble means solid. That means a solid is going to be formed. Then a double replacement will occur. Okay? And here we're kind of bringing them back day one. An insoluble product, that is going to form a precipitant or precipitate. What's a precipitate?
Essentially some kind of
Look at your notes. Thank you.
Oh, it's when two things create a solid.
I need to, you're very close. I'm missing one like big detail in that.
It occurs from a reaction.
It does recur, but you're missing like one word.
Two
There you go. When two liquids form a,
solid.
see that solid there? So if a precipitate is formed, that means a solid has been formed. That means the double reaction has taken place. That means it's a good reaction. Okay? So now what's your next question? Like what else, what's our next step that we need to know to figure out this stuff out?
like how do we know like what is soluble and what is not soluble?
Yeah, what makes things soluble, what makes them insoluble? Because that's the big question with figuring this out. So here we go. All right, these rules that are up here, that's the rules just in a little bit different format than what you see right here. So you're all on this side, right? This is what we're going to be looking at, your solubility chart or rules, table. Makes sense, right? This is what we need to be looking at. This is why I had you take a picture of it so you can use it at home. All right? So, we look at this example. Right? Iron chloride plus potassium sulfide gives us potassium chloride plus iron sulfide. All right? First off, how do we know that these are all aqueous, and how do we know that that's going to be a solid? All right? Here's where I teach you how to use the solubility chart. Ready? When you look at these to figure out, is iron chloride solid or aqueous? You start with your anion, your non-metal. I don't know if you want to write this down, the steps, or whatever you want to do, but this is how you do it. Chlorine. Now let's go to your chart. If you look at the left side is where you're going to start. Look at the left side. Where does chlorine fall? Chlorine's family name is what?
All the halogens.
The halogens, right? So on this chart that you should be looking at right now, find halogens. Put your finger on it. Guys, it doesn't matter if I give you the best chart in the world. If you don't know how to use it, it's not going to help you. So put your finger on halogens on the left side. If you don't know where to look, look at somebody around you's finger. Not everybody has their finger there. Okay? So, that falls underneath what title? Keep your finger there. So what that is saying is halogens, such as those, not just those, but all halogens, will always be soluble. Okay? Will always be soluble, which means they will always be aqueous, unless, here's your exceptions. Drag your finger to the right, to the opposite side of the table, in the same line. I need to see that happen, guys. Halogens will always be soluble unless they are paired up with what? And mercury. See how that works? If any halogen is paired up with one of those three things, it then turns into a what? Which is a solid. Yes, not insoluble or a solid. Okay? That is the basics of how this works. So, chlorine, is it paired up with one of those three?
No.
Exceptions. No, so that's why it is aqueous. So, that explains these two as well. Let's go over here. Sulfur is also called, what's the name of this compound right here? Iron sulfide. Iron sulfide, right? So this is sulfide. Go to your chart. Find sulfide. Put your finger on it. Towards the bottom, right? Sulfides are always what? Insoluble, which means they're always going to be solid, except when they're paired with group 1 metals or ammonium. Are they paired? Is this sulfide paired with group 1 or ammonium?
No.
So it's going to be what?
Solid.
Insoluble, which makes it a solid. Okay? So in this case, since I do have at least one solid, will this reaction take place?
Yes.
Yes, it will. Okay? So how do you do this on a test? Ready for a test question? Or a test-like question? I give you a word problem that says iron chloride is added to potassium sulfide. What you need to do is, first off, figure out what type of reaction it's going to be. Second, you need to figure out if that reaction is going to happen. So if your answer is double replacement, then your next answer should be yes, it's going to happen. And if a double replacement is going to happen, you need to balance it. Okay? So from this is already balanced. But if this were just a blank page, you would need to, your finishing step would be to balance this out. Okay? If it was not a reaction, you would still have the products there because you need to figure out solubility. But you would stop there, put no reaction, and you would not balance it. Because chances are you won't be able to balance it because it doesn't work. Okay? It's not a good reaction. Okay? So don't balance if it's not a reaction, is what I'm saying. Just like your single replacement, once you figure out that no reaction occurs, you stop there. Okay? So here we go. Zinc sulfate plus strontium chloride. All right? First off, what is my products going to be if this reaction occurs? Here's my metals. What I'm going to do, this is what I'm changing there, Aiden. Right? I'm just going to rewrite my metals in the same spots because in my notes the other day it said the anions changed. Okay? So Holly, what's zinc going to pair up with now?
Zinc. It's gonna be
Chlorine. Right?
Oh.
Which means strontium is going to pair up with, what is that? Sulfate. Guys, that right there is one of the biggest reasons why next year all my students will have to memorize polyatomic ions. And why you should start to memorize polyatomic ions, knowing that this needs to stay together. All right? I know you're thinking like, man, I'm so glad you didn't make us do it this year. But it's kind of starting to come back and biting us a little bit by not recognizing that these things stay together. You know what I'm saying? You need to really start focusing on trying to at least memorize a few of them every couple weeks. Okay? So that way your library starts to build up in your head. Okay? Is this good? Am I done?
No.
Absolutely not. I have to make sure I have the right amount of atoms to make these things happy. How do I do that?
Like the first Carl.
I have a metal with a non-metal. What do I need to do?
Check chlorine.
I need to do the charges. I need to do my ionic rules, right? What's the zinc's charge?
2.
Plus 2. What's chlorine's charge? Cross those up. Now I have a good formula. Over here, strontium's charge. Sulfates.
-2.
When I cross those up,
They just cancel out.
they cancel each other out, so that's good. Okay? This is one of the biggest questions I've been having is, like, how do I get my products over here? Some of you just want to, like, copy this stuff straight over and not think about any of your ionic rules when you combine new products. Okay? That's a big part of your homework, and I've been having a lot of questions on it, so make sure you focus on that and ask me today if you need to. All right? So now, is this going to work? What I need you to do right now is tell me the state of matter for each one of these. Technically, we're only concerned with the products to see if this is going to work, but I want you to practice doing all four, just to practice using the chart. Guys, I should not see any phones on our desks. All phones need to be put in our bags. We don't have any calculators. Phones need to be in our bags. All right, so when I look at sulfate is sulfate usually what?
Soluble.
Soluble is zinc an exception.
No.
So this is going to be what?
Yes.
Aqueous. Chlorine, halogen, almost always what?
Soluble.
Except with those, so is strontium an exception.
Nope.
And just a little hint, when we do double reactions in here, your two reactants will always be aqueous. It's always going to be two liquids. Okay? That's why from now on, we're just going to do the products. I just want to practice doing a few extra right now. All right? So zinc chloride, once again, halogens. Is zinc an exception?
No.
So this is going to be what? Aqueous. Sulfide.
Yes.
Is strontium an exception?
Yes.
Yes, it is. The exception makes it solid. So will this be a reaction?
Yes.
Yes, it will. So on a quiz and a test, would you leave that alone?
No.
And go, and go on to the next question. What would you check? What would you do?
Make sure it's balanced.
Make sure it's balanced. You would go through and balance it, and this one looks like it's probably pretty close.
Yep.
Okay? Then you would move forward.
I have a question. Okay, I don't know if he told us about this in our test or whatever, but why does it have to have like one solid for it to be like for it to react?
Because then it just kind of shows us that the liquids mix, like milk and water.
Okay, so if it's all aqueous, it's not gonna react.
Right. There's no evidence of a reaction. Right. Now there's more complicated things and all that good stuff, but just for what we need, no reaction. Okay. The next one. These next two are more like what you're going to have to do on your test. Why? Because they're word problems. Okay. You need to be able to show me you're able to name ionic compounds, and you will also be able to have to write out acids. Okay? So if you can't name ionic compounds or write out their formula, or you're still struggling with acids, you better get on the ball watching those videos again or coming to tutoring or something to practice that stuff. All right? Go ahead. I'll do number 3 with you. All right? So how do I do these? What I like to do is write this above aluminum has a charge of +3 before I start to go down here in my actual work to make sure I'm doing this right. Aluminum is a metal, iodide is a non-metal, so I know it's ionic. Aluminum has a +3 charge all the time. It's part of the exception block. Iodine has a charge of what?
1.
-1. Okay? So I come down here and do this. Guess what? I'm going to have a lot of people be doing that, and it's going to be wrong. When you go to balance it, it's not going to work out. Because it's actually Ali3. Then I have calcium carbonate. Calcium +2, carbonate CO3
-2.
-2. What do those two charges do? And now I have calcium carbonate. Right? On the back of your ionic test, if you remember, you had like 20 questions of naming that and writing the formula. You guys remember that? A lot of us struggled then, but hopefully we're not struggling too much now. That's exactly what you're doing to get these products and reactants. You understand? These will form. Well, what am I keeping in the same place? Your metal. So I'm going to write aluminum here, added to some here, calcium. And then what's switching? Non-metals. So I'm going to put iodine was with aluminum. Now I'm going to put iodine over here. And then carbonate over here, like so. Am I done?
No.
What do I need to check?
Oh, like the
Okay,
the
why
substrate.
didn't you put the
Numbers and balances.
What do I need to do?
Balance it.
Like, make sure the elements work, like, check the subscripts.
I need to check the oxidation numbers.
Oh.
I need to do my ionic rules, right? Now, some of you are saying, like, why did that I put a 3 right here with I? Because that's not how many atoms of iodine I need to be happy with calcium. You see what I'm saying? This is one relationship. Iodine has now switched relationships. Okay? We need to figure out, I go back through and I balance that. But first I need to cross up my oxidation number. So aluminum has what? Carbonate has -2. So when I cross those up, I get Al2.
Need parentheses.
There we go. Yes.
On a Fear's one question, if you put parentheses when I'm not really in the
No. Nope. Calcium has +2. Iodine has -1.
So CII2.
And that becomes a 2. Okay? You see how what we just did here has nothing to do with this unit of reactions, right? Has everything to do with unit 4 ionic compounds, right? I don't know how else I can say that you need to know how to write ionic formulas to do well on this next test. And if not, you're going to struggle. All right, no matter how well you can balance, no matter how well you can name reaction types. If you can't name ionic compounds or write them out, you're going to struggle. Specifically ionic. Some covalent, but specifically ionic. Okay? So from here, are we done? Now we got to figure out solubility. Now, this is where I'm going to say, just do your products. All right? You don't have to mess around with your reactants. So when I look at my products, carbonate. Find carbonate. What is it usually?
Insoluble.
So usually a solid, except if it's
Combined with a bunch of stuff. Like
group 1 and
Uh,
ammonia.
ammonia.
Is aluminum that?
Nope.
So it's what?
Solid.
You sure? You right? Soluble. Or sorry, insoluble. It's a solid. Okay? Just to check over here, what is this one? Iodine is a halogen. Halogens are always soluble with a few exceptions. Is calcium an exception?
Nope.
It is not. Aqueous.
This will happen.
This reaction will happen. Because it will happen, you should now go back through and balance it. But we're not going to spend time doing that right now because we've already done our balancing equation or our balancing lesson. You should be able to go through and balance this. Now, here's a little note. Double replacement reactions, when you go to balance these are the most frustrating. Why? Because they don't have any singular elements to kind of fall back on. Because once you change like calcium here, you've also changed what? Iodine. And this was your question, I think, on the CFA. What can I change up here when I balance? Can I change subscripts?
No.
You can only change coefficients.
Oh, I was just asking if you could do it on both sides.
Oh,
Like
then
just
yes.
the coefficients.
Yeah, only the coefficients. I thought you were getting at something else.
No.
Yes, only coefficients. You cannot change subscripts, even though it may look easier, and it would be easier if we could do that. That's not the right way to do it. Okay? Only coefficients. All right. Right now, you're doing the last one either by yourself or with somebody around you. And don't ask me how to write out sulfuric acid, because the first thing I'm going to say to you is get out your notes from unit 4 and unit 5, because they are in there.
If the 3 is here, there'd just be the I.
Yep. Y'all keep doing this one down here. Keep doing this one down here. Some people are done with this one because they worked ahead, and I'm gonna balance the top one just by writing it out. But I want you to focus on this down here. Watch my steps. Balance those together. Here. Okay, so I'm gonna do my Python counts first. And that messed up my calciums over here. That's 3, that's 6. Good. Now that makes that a 2. That makes that a 6. Aluminum is good. Iodine good. Calcium good. Here you go. Yeah.
For sulfuric acid,
All right. Look to check barium +2, bromine -1. So when I cross those up, BaBr2. Added to sulfuric acid. Every acid starts with hydrogen. But what major word is missing in that term? Hydro is missing, so that means I should be looking for a polyatomic ion.
Yep.
Polyatomic ion from sulfuric is sulfate, which is SO4. -2 charge, +1 charge. When I cross those up, I know that I have H2SO4. Sulfuric acid. Now, when I go to form my products, okay, I've been saying keep your metals the same. However, that's not necessarily true here. What two are we keeping in the same spots?
hydrogen.
Barium and hydrogen, your cations. So barium's going to stay put, and hydrogen's going to stay put. You can go and put their charges above them right away. That way you know you got to do something with them. Then your anions switch spots. Okay? Now watch. Do I go over here and right away put Br2?
No.
No. Because I don't know if 2 barium atoms are going to be happy with 1 hydrogen atom. Does that make sense? So I don't put that. I just put barium. Bromine. Bromine. Now I've also been getting the question, well, that's Br2. Bromine is in Brinkelhoff. Brinkelhoff's diatomic. So why is that not Br2? It's not alone. Your diatomic elements, your Brinkelhoff, they have to be alone for you to put the 2 with it. Okay? They have to be loners. All right? So then I have SO4 here. That's a -2. Bromine was a -1. And lucky, everything cancels everything out. Right? So there are no subscripts here.
Well, except for the one in.
Okay? So, are we done?
No.
What do we need to do?
Balance.
Solubility.
Check solubility. Check solubility. So I should have states of matter put in right here. Anna. VaSO4. Aqueous or solid? BA, so sulfide.
So,
You see sulfide there? Put your finger on it. Down there. Sulfide, right? Is always going to be insoluble, which means it's always going to be solid, except if it's with group 1 or ammonium.
it's sulfate.
Yeah.
That's why,
Sulfate.
That's why it's a solid.
yeah, it's a, but
Sulfate.
it's still a solid.
I'm sorry. Sulfate.
It's like
A little higher.
sulfate.
Sorry.
Soluble, but
It's always going to be soluble, which means it's going to be aqueous, unless it's attached to BA is an exception, right?
yep, and so that's solid.
So that's going to turn that into a solid. And that's a terrible S. Solid. All right. Now over here,
That's a halogen.
now number 1, I should see that that's an acid, HBr, and acids are always going to be aqueous. However, if you didn't notice that, bromine is a halogen. So look at your halogens. Halogens are always soluble,
And hydrogen is not a.
and hydrogen is not an exception. So this is going to be aqueous. Okay? From there, you would do what? Balance. You would go balance it if you could, and most of the time you will need to. Okay? The last thing, the most fun thing, is balancing combustion. So, up the first 4 that we talked about, to balance them out, you just kind of find a problem and you fix it. Okay? Your first problem that you find, it could be different than what I want to fix first. It doesn't matter. As long as you go back and forth and fix everything, you're going to be good. There's really no rhyme or reason that you need to follow. You just find a problem and you fix it. When we go to combustion reactions, you need to do it my way. Okay? And my way is the easiest way and the most foolproof way if you do it right. And if you don't do it my way, you're going to get very frustrated. I promise. Okay? So here are your rules. You need to do it this way in this order. Okay? You are going to have to memorize these rules, but there's only 3 of them. The bad part about being 3 of them, the first one's like 5 and 1. Okay? So, I'm going to read it to you, but it's not going to make sense until we do it. So, don't get too mad. The first thing is you balance out your hydrogens. You balance out your hydrogens. Here we go. When you balance them out, if the coefficient you add on the product side, so on the right side of the arrow, if that coefficient you add to the hydrogens to balance it out to the left side is an odd number. So, when you're going to balance it out, you write down a 3. 3 is odd, right? Continue reading. Then double it. When you double it, you write that number down, and then you have to go balance back on the left side. Okay? This probably doesn't make any sense right now. That's fine. You go and balance on the left side. And that's it for the hydrogens. They should be balanced. Then you balance your carbons, then you balance your oxygens. Carbons first, oxygens last. There's a reason why oxygens last. Alright? So let's try one. We have this. You ready? What is your first rule, Jacob? Your first off, you notice that this is what type of reaction? Because of all the components, right? Once you know that it's combustion, what is your first rule in balancing it? Balance what one? Look at your notes, man. Your notes are right in front of you.
It's just on the page before.
We just did it. You just wrote it down.
Thanks for balancing.
So what do we do first? hydrogens, right? So how many hydrogens do I have over here?
6,
How many do I have over here?
2,
2. So what number can I put up here
3,
to make it a 6? To make it 6?
3.
3. However, read the note, read the step.
If it's odd, you have to
If it's odd, what do we do?
Double.
So I double that and put a 6. That was the part that really confused my last class. Okay? So now no longer do I put a 3 there, I put a 6. I think their confusion was, well, 3 balances it, why am I putting a 6? My answer is, this will save you a lot of work coming back to it. This will be a lot less ping-ponging back and forth if you double this right away. If it's an even number, you leave it. Okay, so if that happened to be a 4, you just put the 4 down. Okay? So now that it's a 6, how many total hydrogens do I have over here?
12.
Which means I need to come back over here
Make that a 10.
and balance my hydrogens again. Make this a 2, and now are my hydrogens equal?
Yes.
Yes, they are. That's the only time that I do the whole odd double number thing. If I happen to write any more odd numbers up here, I leave them. Okay? That first step on the right side with the water is the only time I double that odd number. And once again, it's just because I want to save myself more work or less work moving forward. Yeah. Because that's what would have balanced it right away. See how there's 6 over here? 3 times 2 is 6, right? And that would have balanced it right away. And that's been like the issue. But what I'm telling you is, if you just put that 3 there, it's not going to be balanced at the end. Now that you have the 6 there, it will be. I'm saving you a lot of work if you just trust me on this, okay? So, my hydrogens are good. What's my next step?
The next one is the carbon.
Carbons, right? How many carbons do I have here?
4,
How many do I have here?
1.
Well, what do I need to do to balance my carbons?
Make that a 4.
Are my carbons balanced? Yes? Oxygens. How many do I have here?
2.
How many total oxygens?
14.
4 times 2 is what?
8.
6 times 1? 6 plus 8? 14. How do I make this oxygen?
7.
And you have a balanced equation. Thank you. I didn't come up with it. I just teach it. All right, clear as mud? Yeah.
Why don't you change the 7 to an even number?
That's where, you know, you might want to write this down, is the only time you do that double the odd is for your very first hydrogen. And then from there, if you have any more odd numbers, you leave them. Okay? Leave them. Just trust me on that, okay? Now, once again, let's say you don't trust me, and that's fine. That's fine. And you wanted to keep that 3 there without doubling it. You could go and start to balance it. However, you would be going back and forth a couple times, and you would eventually get that number to be a 6 to make it work. Okay? You can do it if you got some spare time tonight, don't have a date on Friday or Saturday, do some chemistry. All right? Yes? Now, here's where you think I'm going to blow your mind, but I'm really not. If I said, what's the coefficient ratio of this equation? And I could ask this about any equation. What's the coefficient ratio?
4 to 14. No.
Let's say I have, in my house, I have 2 cats, 3 dogs, a fish, and a turtle. What's my ratio of pets at home?
2, 3,
What's my ratio of pets at home? 2 to 3 to 1.
So it'd be 4 to 12.
What's my ratio of coefficients?
4 to 12 to
4 to
14.
6.
What's my ratio?
2 to 7.
2 to 7 to 4 to 6.
That's nice.
Now, why is that important? Why is that something I'm teaching you? Number one, I just saw it on the test. Okay? Number two, what we're actually saying here is I need, for this reaction to occur, think about this like, why are you learning this? Well, some of you might grow up to be going to some type of chemistry field. Okay? Whether you think about it or not, I never thought I was going to be a chemistry teacher ever. Okay? Here I am. Right? But what this is saying is, let's say that this is not methane. Let's say it was methane. Okay? How much methane and oxygen do you need to put together to get this amount of products?
2 to 7.
Okay? Or let's say like you're a demo person, or you're selling this stuff, and you need to be able to report if you use this amount of methane, you should expect to be able to deal with this amount of water at the end. You see what I'm saying? Like I'm selling this chemical here, right? And to be able to sell it, I need to be able to express the products or the what you're going to get out of it and be able to deal with and dispose of the right way if you need to dispose of it. Yes? Or emissions. Anybody drive a car right now? About to drive a car? You have to get it checked every year, right? Emissions, right? This is kind of not necessarily exactly what it is, but you need to be able to tell you how much emission it's going to give off to be able to deal with it. Okay? So for every 2 of those, it needs to react with 7 oxygens. And if you don't have 7 oxygens, it's not going to work. Okay? That's where the ratio numbers come into play. All right? And we'll do it a lot with those ratio numbers next semester. Okay? But you will see ratios on your test coming up. Nothing more than that, but just so it's not brand new to you. Yes?
Can the numbers ever go in a different order?
No. Whatever's listed in this way, just like if I said my ratio of pets at home is 1 to 1 to 3 to 2, that doesn't really help you out because you don't know what order the pet name is. You know what I'm saying? So it's got to be in the order of how you read it across the table. Okay? Now, what you will see more likely on your test, once again, is word problems.
Oh no.
And it can be very simple as not even combustion of propane. I could say, I go out and light my propane grill. What's the chemical formula for it? What's the key word in there? Ignite, light, burn, combust. Because all of those words tell you to go to what reaction? Combustion. And with combustion, you know all of the components. What are those 3 components that are implied up here? Oxygen, carbon dioxide, and water. You see what I'm saying? At first you thought, man, you're not giving me anything. You're not. I can't do that. You're not giving me enough information. However, ignition, ignite, burn, flames, explosion, light. I don't know. Maybe I said that again. Right? Those all tell you that you have some type of combustion. Yes? And now you know that combustion always has oxygen with some type of fuel. In this case, I will always give you the fuel. All right? You don't need to memorize hydrocarbons. Does that make sense? Now, can you balance that?
Yes.
Well, you have the ability to. If you can or not, it's a different story, but you've been taught and you have the ability to do that now. Okay? And then the same thing down here. Combustion of propane. I'm telling you right now, there's a couple examples that I remember. It's not going to say combustion of propane. It's going to say, I went out and lit a firecracker, and this is what happened. Or I went out and did this, or a candle was burning, and this, whatever, even though candle's not a hydrocarbon. But you see what I'm saying? In the word problem, like just like in math, somewhere in there it's going to say burn, fire, flames, explosion, something like that. You need to think straight to combustion. All right, so then we have this one, O2, CO2 plus H2O, my hydrocarbon.
I actually spelled it.
There we go. All right, go ahead and try to balance both of those now.
Also, like,
Hmm?
when we're done with it, right on the board.
It's always because that's oxygen. Oxygen is what type of molecule or atom?
I get it though, you're saying.
No, you don't.
So do you. I don't understand. It's always
Because, let's see if you do. You ready?
Oh, this is. Stop.
Write out that chemical formula. Or that chemical equation. Could you say you understand it?
Well, I get it. I get what we're doing right here. I can solve this.
But that doesn't answer your question of why is it O2.
No. It's hydrogen. I don't know. I don't know, I get it. I was doing this problem.
It will always be oxygen right there.
God.
But just because it's oxygen doesn't mean you understand why it's O2. But do you? What's the chemical equation for this? H2 plus O2. Why?
Because it's a
Brinkelhoff. Those are both diatomic molecules, which is why this will always be O2. Because oxygen is by itself. That makes sense now? Good.
So I think I actually just solved them both.
Good.
So whenever like on the first rule for hydrogen, it was like whenever it's odd, you have to double it. Is that for the carbon and oxygen or just hydrogen?
Just the first hydrogen. Here we go. I'll do it up here, and you can watch if you're done, or check if you're still finishing. Hydrogens, I have 4. To make hydrogens 4 over here, let's do that. 2 is even, so do I need a double?
No.
No double. So now I have carbons. I have 1 carbon here. I have 1 carbon there. Carbons are good. And then oxygens, I have 4 over here. There's 2 there. There's 2 there. I have 2 over here, so if I put a 2 as that coefficient, there's your balanced combustion equation.
And you have a ratio.
So when you're writing the ratio, do you put the 1 at the front?
Yes.
Okay.
Yes. So if I say what's the coefficient ratio, or the molecular ratio, the how many molecules of each do I have?
It'd be 1 to 2.
1 to 2 to 1 to 2. In that order.
Oh.
The implied one. The implied one. The next one, H10. This is a good one. Question? Good. H2, to make it 10, I need to put a 5
You gotta double
in
that.
there. That's odd.
So you gotta
It's not
double
odd, it's an odd number. Make that 10, because I double it.
That makes that hydrogen.
So now I have 20 hydrogens on the right side.
You gotta put a 2 coefficient.
And now over here, if I put a 2, that makes that one 20.
Yeah, but now you got 8
All right.
on that side.
So my hydrogens are good. If I look at my carbons now, I have 8 carbons. I have 1 carbon here right now.
You gotta put an 8 coefficient.
If I put an 8 here to fix that, which it does, now I have quite a bit
26 oxygen.
of oxygens. 16
16.
plus 10, 26.
13 coefficient.
Well, the good thing, and now hopefully you can see, why do we balance oxygen last?
Because it's all by itself.
It's by itself. It's kind of the easiest one. So like if I get everything else right, I can pretty much put whatever number I need to with oxygen to make it work.
13.
Okay? And I put a 13 there, which makes oxygens 26. Now once again, do I double that number?
No.
No, if I double it, then I've just screwed everything up. Right? I screwed everything up. 13 makes all of this work. The only reason I double that first hydrogen is because I'm telling you right now that if you don't, you're causing more work for yourself in the future. Okay?
It's kind of easy. once you
Now,
do it.
I promise you that if you don't do the homework tonight and this weekend, come Monday, your quiz score is going to be just like your last 2 quiz scores for most of you. 30s, 40s, 50s. And if you think I'm joking, hopefully by now you've gotten a few kicks in the pants of if you don't do the work, it's not gonna help. Nothing's gonna happen for you. Now those of you that chose to sleep all day today, luckily for you, there's videos online. Or if you just need to hear something again, the videos are online. Please go look at them.
There's a pencil.
You know, I was kind of worried from the beginning because I was so lost. But